Okay. Now where did it go? All right. So we did things like sodium and oxygen, and you'd draw the picture for sodium and you'd show that it lost 1 electron, and you draw oxygen and show that it gained 2, and then like you would have to know that there's 2 sodiums for every 1 oxygen. So we did do like some really introductory basic stuff. It's pretty much review from chapter 3 for ionic compounds. So just don't forget that that was part of the beginning of chapter 10. Then everything else after that, I'm sure you're not going to forget it because we've been doing it the whole time. So this is drawing Lewis structures, making sure to indicate if there's resonance. You'd have to have multiple bonds. Maybe like a little bit of things that you might have kind of forgotten that they're a thing. Like if you have a charge, you have to either add or remove electrons. We talked about bond order when there's resonance, like knowing is it a single bond or a double bond, or is that additional bond spread out over multiple bonding regions. So we'll do an example of that today as well. A little bit on formal charge, although we didn't have to use it nearly as extensively as I usually do. You still need to be aware of it. And then we get into chapter 11 stuff that's all dependent on those those Lewis structures. Okay, so I think what I want to do is just quick discussion about formal charge, and then we'll do an example, and I'll make sure to do resonance. There was a question about how much do we need to know about dipole moments and electronegativity differences. That same question came up in my other class as well. So we'll hit that a little bit, and then we'll do like maybe 3 or 4 molecules, and we'll use those as examples talking about hybridization and sigma and pi bonds, okay? You don't have to know, like all of the stuff I said in the video, a lot of that was very background information, and it's definitely important, especially if you're going to go on and take organic chemistry. But I only have 20 questions on the exam, right? If you haven't taken an exam for me, that's another good point. There was that question too. So multiple choice, completely multiple choice, like bubble, fill in. I'm not even going to save your exam. So there's no partial credit, which is annoying for you, but there's also, you can guess, right? It's 20 questions. Because it's not math, it won't feel long. Like the math ones, when there's 20 questions, feel long because it takes you a lot of time to calculate them. This won't feel rushed, I don't expect. You have the whole class time. What else? Any other thing I didn't cover about format? When you're doing the practice exams, that's not really format, it's part of it. So those are both due Thursday night. You can take just one attempt, and that's fine. But if you want to take a second one and improve your score, it'll just take the highest, not like an average or anything. So even if you just want to go in and like look at a couple questions again, I guess you can look at them. Yeah, you can look at them either way. Let's say you're happy with your score on the first attempt and you want to know what the right answers are. Just open up the second attempt and pretend to do it. Click a couple things and then submit it. That way it'll then let you see the correct answers, and a lot of them actually have explanations as well. So that's kind of a way around it if you just want to make sure that, I don't know why you would do that though. Because if you've missed enough that you're worried about what the correct answer is, you probably should try to get them correct the second time. Okay, if you have questions on the practice exams, the best way to do it is take a screenshot. You can tell me, like you can't say question number 5 because they are randomized, but you could say like exercise 11.12 or whatever, and I can go look it up. But the easiest way is to take a quick screenshot and then just email it to me and be like, this is what I did and I don't know where to go from there, or I don't understand such and such. I'm happy to answer those. Even though it's for a grade, like I don't care if you don't understand something and want me to walk you through it. That's fine. Okay? I think that's all of those kind of things. Yeah.
Can you click off the practice exam? You have to do it in one sitting.
Does anybody know the answer to that? I know there's not a time limit, but I would worry that if it disconnects, like from an internet connection, that it would think you finished.
Yeah.
That's my guess. So yeah, let's say one sitting, but there's not a time limit.
Yeah.
Okay. All right. So quick note about formal charge, because we didn't use it to determine a whole lot of like what's the best Lewis structure. If there's ever a question, you can do that. But we didn't end up having to most of the time. So the other way that it could be used, though, is to actually say, here's a structure, what's the formal charge? Because it is a concept you need to be aware of if you're given Lewis structures, not asked to draw one, and you want to know which is best, okay? So the way we do formal charge is you separate out a bond into the two electrons, giving one to each atom that it's attached to. And then you look at the atom that you're talking about and say, how do the number of electrons it has now, how does that compare to what it started with? So carbon originally had 4 electrons and now it has 5. So we would say that it has a -1 formal charge because in the process of going from an atom to a molecule, it gained 1 electron. It went from 4 to 5. And then oxygen is the opposite. It started with 6 electrons and now has 5. So it lost an electron, so it would be a +1. Okay, so just a quick review if you forgot what formal charge is, how to do it. Ideally, in a molecule, everything has as close to 0 as possible. If you have to have formal charge, usually you want that on the more electronegative atom. Carbon monoxide is like the one that breaks all the rules. You end up with the negative charge on the more electronegative atom. It's because that's the only way you can satisfy the octet. Okay? But that's the general thing with formal charge, is how to assign it, and then you use it to decide if you have 2 possible Lewis structures. You pick the one that has the charges that are closest to 0, or if there are charges, you want the negatives to be on the more electronegative atom. Okay, the other question was kind of about like dipole moments, polarity, difference in electronegativity. Those are all different ways of looking at things. So like if I have HCl versus HF, and it asks me about, like, let's say it says which has a larger dipole moment, okay? That is the same thing as saying which one has a bigger difference in electronegativity. Or another way you could say that is which one has, like chlorine or fluorine, which has the bigger partial negative charge. Okay, all of those things are related. So the place you want to start is the electronegativity. You do have the chart in the exam equation sheet. So that is stapled on the end of your exam. A fresh copy, 4 pages worth of all that additional information. It's, if you don't have it downloaded already, it's on Blackboard. It just has the original file, so you know exactly what you have. But you're going to have that table, and you would just go look up the electronegativity values and say, okay, hydrogen's 2.2, chlorine's 3.0. So the difference in not H, there's another delta H that we use all the time that we haven't even talked about yet. The difference here is 0.8, whereas for HF, it's 2.2 and 4.0. So the difference in electronegativity is 1.8. So knowing that, we can say HF is more polar. We could also say it has a larger dipole moment. These all mean the same thing. It has larger partial positive and partial negative charges. And then like making sure that, you know, you remember the visual way that we represented these. So like if you're drawing an actual arrow for a dipole moment, that would be physically bigger on HF. I guess the one other way we drew it was like with the electron clouds is the official word, but like, you know, a depiction of, okay, now I drew that one too big. Now I'm gonna have to draw this one enormous. a depiction of where the electrons reside. So in HF, they're spending even more time over by the fluorine than they were with H and chlorine, okay? You're not going to be, well, it's multiple choice, so you're not going to be drawing the dipole moments, right? You're not going to be like summing them up in a molecule with multiple bonds. Okay. All right. So now let's go ahead. I'm going to use, let me make a list. They're the same molecules that I did in the other class. I did SO3 2 minus, SO3, ICL3. I can't remember if there was another one. So we'll start with that. So go ahead and start with SO3 2 minus, and I want you to draw the Lewis structure, a complete Lewis structure. And I want you to tell me all the stuff. So electron geometry first. Molecular geometry, angles, is it polar or nonpolar, hybridization of the central atom. And then I guess the other thing we could do is how many sigma and pi bonds are there. So we'll do this first, have you guys do it, give you a couple minutes to do it, and then we'll talk through it with a lot of detail about hybridization and sigma and pi, just to make sure you're comfortable with that, and then we'll do the last two, okay? So I'll give you guys a few minutes to do that, because that is kind of a lot of stuff.
Specifically about the molecule polar thing. Does it tend to be like where it's not polar if like there's no lone pairs within the molecular structure?
That is a good place to start. So as long as all the atoms that are on the outside are the same, right? Like in this picture, those are all chlorines, right? But like what if one was a fluorine? Then it definitely would be polar, because like you can't cancel them out if they're different things. Because they're gonna have, just like we showed with HCl, like they have to have the same size of difference.
So I guess there's an exception to if there is no lone pair if you have like more than two elements.
On the outside, yeah. Oh, more than two, yes.
Yeah, so like for example, trying to think of something. So like, something like that.
Yeah, that's perfect.
CH2O. So
Yeah.
that would be that, because it would be have an additional one instead of just H2O.
Right, yeah, like if it was CO3, which we have CO3 2 minus, that's similar, then it would look the same, because all of those ones are trigonoplanar, so there's no lone pair, and they're all kind of spaced equally around. So if it was CO3 2 minus, it would be nonpolar, but because two of those groups are now hydrogen at CH2O, then it would be polar.
Yeah.
Because, like I said here, they're not equivalent to each other. They're not the same amount of difference of charge. Now, to be careful.
Now, the one thing I was wondering is like, what's a CH2O structure like? That like, does the C attach to the H or to the O?
The C is in the middle. I make sure to tell you that kind of stuff on the exam if it's unclear. But in this case, you know it has to either be the C or the O, because each can only ever have one bond to it, so it can never be in the middle. And the reason you know it's the C and not the O is because carbon is the one that forms more bonds. Usually oxygen just has one or maybe two bonds, three at the absolute most. Carbon it always has.
So would it be? I mean, obviously excluding like total bond load, would it be something like that? Hydrogen like here, then oxygen.
Yep, and it's double bonded.
Yeah.
Yeah.
Obviously including the double bond, but
Yeah.
So,
Now, when you do these though, you're drawing out like the valence electrons and then
Yeah.
you're them, right? Okay.
yeah.
So I wanna go back to this though, because you said if there's lone pairs, does that mean that it's polar? So this is a really good example, because this one does have lone pairs, but this will actually be a linear molecule. So it'll have all three of those lone pairs will be in the middle plane, and then it'll have the two iodines up and down. Now technically that isn't a polar bond, but let's pretend it's with like, I don't know, chlorines or something. Even though it has lone pairs, that doesn't mean that it's gonna be polar, and there are a few exceptions. If you look at that chart, I don't know if you have it written down, or if you have, probably not, that would be a lot. But if you look at that chart from the examination sheet, where it like
Oh, yeah, I
shows-
think I
Yeah.
have that.
And in fact, I think it's in the notes here. I can pull it up.
That was just me saying, you know, let's check and see if people are done. Let me pull up the one that I'm thinking of, though. If it's in these notes, it could be in a different class. I like color coded it so that, okay, it's this here. So these three are ones that have lone pairs, but that will still be non-polar, assuming that like those are all the same atom. So as long as you don't have three different types, right? But even though they have lone pairs, then they're still non-polar. So I'll leave that up there for a second. All right, just one more minute and then we will go over SO3 2-. If you've already finished it, just move on to SO3 and then we'll come back to talk through it in a second. Oh my gosh. Did anybody else fall on the ice this morning? Okay, 5 people in my family, 3 of us fell down. My daughter was so bad, she was walking to the bus stop and she comes back and she's like, her hands are all bloody. She's like covered in mud. I had to like get her cleaned up, drive her to school. So I'm like rushing around. And then my stupid little boys, love them to death, are like screwing around on the ice and like sliding down the driveway. And one of them falls down. And I run out there to like, because the bus was about to come. So I run out there to be like, are you okay? And then I fell down, totally slammed my shoulder. Like, I swear I'm going to have to like put it in a sling today or something. Can hardly write. It's ridiculous. It's like nature is laughing at us. It's 55 degrees yesterday, and it's like, oh my gosh, it's gone. It's leaving. It's going to all melt away. It's like, psych. Here's this ice. Fall down on your ass, please. So 3 of the 5 of us. It was great.
That's what happens when you get all that leftover water after.
I know. I know. And we're like really good about salting, but apparently I did not think of that yesterday. Just didn't even cross my mind.
I've seen like less salting on growths this year. I don't know what.
They're
that's
conserving
about.
it because
Yeah.
there hasn't been enough. Like they didn't order enough and some places can't get it and they know that it's been worse, so they're like trying to conserve it. Yeah, I've noticed that too. Okay, you good with this chart now?
Yeah.
Okay. All right, so SO3 2- looks like this. It's got a lone pair. So remember, this is a 2-, meaning we had to tack on additional electrons, 2 additional electrons. They should go to an oxygen. 2 of the oxygens, in this case it was the 2 outer ones, would have gained those electrons. And so your structure should look like this. There should be a lone pair on the sulfur, and it should have resonance, okay? I'm going to do it because I feel like I need to emphasize the point just to make sure, since we're right before a test, but it is a pain to draw it all over again. So 3 equivalent bonding regions, which means I'm going to have 3 resonance structures. Now, I feel like it's unlikely that I'm going to like draw, like say, which is the best representation of SO3, and I'm going to draw 1, and then I'm going to have one of the other choices be 3 resonance structures, because that's like, well, duh, she's telling us like there's resonance structures. So more likely, a way I would ask this question is I would say, I don't know, here's a list of 3 molecules. How many of them or which ones of them have resonance structures, have more than one, possible structure. Yeah. So I guess another way I could ask it is like SO3 2-, how many resonance structures exist? So then you'd have to draw it and make sure that you know that there's 3 resonance structures. Okay. Another thing I could ask about this is what's the bond order? So we talked about this a little bit. So when you have resonance structures, that means that you have to take that additional bond and spread it over all of the bonding regions. So each one of them has its one bond, and then that additional bond gets spread over 3 regions. So it's 1 1/3 bonds. Okay, so that's the bond order. Yeah.
Is bond order only asked for when there's a resonance?
Not necessarily. It's just the time when it's not a whole number. So like we might talk about bond order with a double or triple bond, but usually we just say double or triple instead of saying, I don't know how you would say 1 1/3 bonds. Yeah, I guess you would just say 1 1/3 bonds, but we don't usually say a bond order of. So good clarification. Okay, and then electron geometry, 4 regions. So first thing, you got to remember the number of regions is so crucial because it tells you like at least 3, if not 4 pieces of information, like answers to these questions. So this is a great example because we've got a lone pair, that counts as a region, a single bond, 2 of those regions are single bond, a double bond, the only thing that's not in there is a triple bond, right? But those are the things that count as one region. A lone pair, a single bond, a double bond, a triple bond, those all count as a single region. So 4 regions total. Space those out equally, you get tetrahedral for the electron geometry. Is that a different number? Tetrahedral. The molecular geometry, because one of them is a lone pair, that's trigonal pyramidal. The other thing you knew, once you knew, let's do that first actually. You knew electron geometry from the 4. You knew the angles were pretty close to 109.5. We don't know exactly until we look at the molecular geometry. And we know the hybridization. Okay, we'll get to that in a second. But all you have to know to determine hybridization is the total number of regions. Okay, so the angles are actually just a little bit less than 109.5 because of that lone pair. For polarity, it's a pyramidal shape because that lone pair is there. So it would be polar because you have those equivalent bonds, the SO polar bonds, but they're not able to fully cancel each other out because their geometry is not it's not symmetrical. There isn't one on the top to balance out those 3 that are in the pyramid. Go back to the tug of war analogy. Okay, so now let's talk about hybridization and then the whole sigma and pi thing. So let's do sigma and pi first. It's easier, just like the numbers. So there's 4 types, I guess 2 types of questions per topic that I could ask you about. There's the easy question, which is like, how many sigma bonds does this have? How many pi bonds does this have? Okay, so we'll do that right now. And then I could ask you, what's the hybridization of, in this case, the sulfur? I'm always asking you about the middle atom. If it's a more complicated atom, then I would have to specify, like this carbon or that oxygen. So what's the hybridization of sulfur? And that's like sp. sp2, sp3. When I ask what is the hybridization, that's what I'm looking for. So those are kind of the easy versions of that topic. The difficult version would be more about what that means. So maybe I have a question that says, select the best answer that describes the difference between a sigma bond and a pi bond. Okay, so it's more of a concept-based question. Same thing with hybridization. I could say something like, looking at an sp3 orbital, would you anticipate the energy being closer to an s orbital or a p orbital? Okay, I only have 20 questions that I can ask you. So there's no way that I'm going to use 4 of those 20 questions to ask you an easy question about hybridization, a concept question about hybridization, an easy question about sigma and pi bonds, a concept question. Like, I just don't have time for that. So don't stress too much. Like, study it, obviously, but don't be freaking out about this new thing that we learned on Monday, because it can't possibly be that much of the test because there's all the other things too. Okay? So that's like your first reassurance. Second, I'm probably going to focus mostly on the practical assigning hybridization, determining sigma and pi bonds, less on the higher level concept stuff. Maybe I ask one question about that for the whole, segment there. Usually concept questions are like maybe a couple per chapter. I've got 20 questions, maybe ask 2 or 3 total concept questions per chapter. Even that sounds a little bit high. Okay, let's talk sigma and pi bonds. So don't even think about what they are yet. We'll talk about that in a second. Just counting them up, a sigma bond, the first bond to form between any 2 atoms is a sigma bond. It's low in energy, and it's just the one it's like the normal bond that would form. So let's say this one, that one, and this one. I'm just picking one of those 2. Those would all be sigma bonds. So I would have 3 sigma bonds in this molecule. If I have a bonding region that has more than 1 bond, I have to have a different bond type. That's when I would have a pi bond. So in this case, one of those in that double bonding region would be a pi bond. So one's a sigma and one's a pi. So in this question, I've got 3 sigma bonds and 1 pi bond. If you had a triple bond, so like we did CO earlier, okay? So there's just that one region. One of them is a sigma bond. The other 2 are pi bonds. You cannot have, this probably will make sense when I tell you the concept side in a second, but you cannot have 2 sigma bonds in the same place. So let's use the CO as an example. So the original Lewis structure looks like this. And each of these, I'm going to pull in hybridization first, okay? So they're tied together because of what orbitals they use to do the bonding. So let's talk about hybridization of the SO3 2-, and then we'll use CO to talk about hybridization as well, okay? So the hybridization is completely dependent on how many regions you have, because however many regions, you need that many equivalent orbitals. So the orbitals we have to pick from are an S, 3 Ps, and sometimes 5 Ds. If we are at n equals 3, our valence shell, if it's at n equals 3 or higher, then we have d orbitals as well. So we take however many, in fact, I'm going to write this down. So we count up the number of regions. That same number of regions, that's how many orbitals we're going to mix together or use to make new orbitals. So I'll say orbitals to use, and that's going to equal the number of orbitals that we make. So new orbitals made. Okay, so for SO3 2-, and I just saw a flaw of using CO, so we might have to switch that to CO2 in our example in a second. Let's stick with SO3- for now. So for SO3-, we said there's 4 regions, okay? So that means I need that same number of orbitals to use to start with. So I always start with the lowest energy one. I'm always going to take an S, and then I take however many more I need, working my way up through the P's and the D's. So in this case, I'm taking the S and all 3 P's, and I'm going to mix them together. This is where I start to lose people because they're like, what does that mean? It doesn't mean anything, okay? There's no one is coming in and mixing orbitals for SO3. It is a way we describe what happens because when we look at SO3, we know it has 4 orbitals surrounding the sulfur. We know that they don't look like the original s orbital and the original p orbitals. We know that they're in a tetrahedral shape. And what's probably the weirdest part of it is that the new orbitals that are made, that are there, their energy is between S and P. So these are my new ones, but they're a little bit closer to the P. Their shape looks a little bit like the S and a little bit like the P, but it's a little bit closer to the P. Okay? Because I mixed in 3 P's, right? It's like dominant in P. There's a little bit S and a lot P. So the shape is a little bit S and a lot P. I'm very much getting into the concept side now, okay? The energy is a little bit S, but a lot P, okay? The way we label these, like the name we give them is, and go back to this, however many you have, you're going to write that down as a superscript. So in this case, we used 1 S, we used 3 P's, and we used 0 D's. So I'm going to rewrite that as SP3. Not going to write the D's because they aren't there. I'm going to forego the 1 just to save myself some time. So when you look at SO3 and you're asked, what is the hybridization? All you have to do is count up the number of regions and say S, P, P, P. Okay, SP3. All right? If you had something like this, 3 regions, S, P, P, so this would be SP2. Something like that, 2 regions, right? S, P, that's the hybridization. You literally don't have to do more than that when you're just assigning hybridization. So that would be like the easy side, the like most basic type of question. I guarantee you'll have at least one question where I say, what is the hybridization of a particular atom in a particular molecule? Maybe I show you the molecule, maybe you have to draw the Lewis structure, but you're certainly going to be asked to assign the hybridization. Yeah.
How would you determine what that is then based on?
The number of regions.
Like,
Yeah, just like I did. Yeah. SP for this guy because it has 2 regions. SP2 because it has 3 regions. PF4, I think, looks like this. 5 regions. 1 S, 3 P's, 1 D. So SP3D.
One thing I wanted to bring up was this idea that you can't have a hybridization of 1 region. I don't think.
That's right. Well, technically, nothing has 1 region. So, like, I started to talk about CO, but then I was like, oh, I don't want to do that. So C actually has 2 regions, right? If you just are looking at the carbon, we would never really talk about this one because it's almost too simple. Like you can't talk about bond angles, you can't, but it still does have 2 regions. It has a bond and then it has a lone pair. And nothing will ever have 1 region because there is no such thing as like a quadruple bond, and you wouldn't be filling the octet if you didn't have 4 regions. So yeah, you'll never have anything that has a single region.
Yeah, so even something like carbon monoxide is still going to have multiple regions.
Yeah. Yep. So the carbon would have 2, the oxygen would have 2. We would actually technically say both of those are SP hybridized.
Yeah.
SP. No such thing as SP4 because there's not 4 p orbitals. So you take however many you need, knowing you get to start with an S, add in P's as much as you need, up to 3, then go to the D's. And that's why it corresponds so closely to the chart, right? The chart is in order of like 2, 3, 4, 5, 6 regions. So it's SP, SP2, SP3, SP3D, SP3D2. Okay, let's use, okay, so do we even answer? I think we answered sulfur. So sulfur is SP3 because it's 4 regions. So I want to talk about CO2 as our example of how does hybridization now play into sigma and pi bonds, okay? So let's just look at one side of CO2. So we'll take the left side. So carbon itself, 2 regions, sp hybridized. So it started with S and P. I used 2 of those and made 2 new orbitals. So I'm going to label those sp and sp. But like, notice I used 2 of them. I still have 2 p orbitals left over. Okay, I didn't use these other p orbitals. And carbon has 4 valence electrons, and they all are participating in bonding here, right? They're not any lone pairs. So what happens is that on carbon, you have a lone electron that's going to form a bond with the oxygens in those sp orbitals. So I'm going to try to draw you a little picture-ish of what it looks like. So you've got an orbital that's right in between the carbon and the oxygen. So there's 1 electron in there on the carbon, and then the oxygen comes along with its orbital and it overlaps with it. That is a sigma bond. When you have 2 orbitals, they're specifically hybridized orbitals, and they overlap directly between the 2 atoms, that's a sigma bond. That's how they share electrons. Initially, that seems like pretty obvious, like, right, what else would they do? Okay? But that is the most basic, lowest energy type of bond that we see. So in a concept type question, describe the difference between a sigma and pi bond. A key point of a sigma bond is that they are directly overlapping between the 2 atoms, between the 2 nuclei. They involve hybridized orbitals. Whereas a pi bond, so I'm going to erase what I drew with the sigma bonds. A pi bond, so one of these is already done. We've already done that as a sigma bond. The second in this region can't go directly between the 2 atoms because there's already something there, okay? So a double bond happens, but in order to reduce any electron repulsion, it's not going to happen in the same physical space, like right between the atoms. It goes a little bit away from those nuclei. So here's the p orbital on carbon, and there's also one on oxygen. I'm not going to draw that out, like where it is. I'm not going to draw out oxygen's hybridization. Just trust me that there's a p orbital. So those p orbitals that I said were like left over from the carbon, they have an electron in them, and they get shared. They just get shared a little bit outside of that direct between the nuclei region. Okay, so there's 2 spaces. That's just a single bond. Not a single, I shouldn't say the word single. It is 1 bond. So 1 is in the middle. That's a sigma bond. And then the second of the 2 is top and bottom, kind of a little bit away from the nuclei themselves. So that bond happens to be a little bit higher in energy. It's a little bit more reactive. Like if something else comes along, like chemically, it might react a lot easier than the sigma bond would. And if you have a triple bond, you'd have to have another p orbital on each and overlap those as well. Okay, so that's like higher order concept of both hybridization and sigma and pi bonds. Lower level questions are, what is the hybridization? How many sigma bonds are there? How many pi bonds are there in this molecule? That sort of thing. Again, I'm not going to be able to ask you that many concept questions if there's only going to be 4 or 5 concept questions on the test, right? Okay, let's do one more. I want to do ICL3. So I'll do it up here. You guys go ahead and take a minute and do that as well. And do all the stuff, electron geometry, molecular geometry, et cetera, et cetera. I think I said I'm not going to ask you angles about these ones, but I'm putting it there just for interest's sake. Just in case you did SO3 earlier, if you had an extra time, I'll just put that down here. If you didn't, you know, no problem. You can copy it down for extra practice if you want, but okay. So Only things that are kind of new here, hybridization, 5 regions on the top one, so 1 S, 3 Ps, and a D. On the bottom one, 3 regions, so S, P2. Sigmas and pies, the top one, 3 sigmas, no pies. The bottom one, 3 sigmas, 3 pies. And then all the other stuff should be becoming pretty darn familiar at this point. Okay? I think I said I won't ask you about angles of the one that's on the top. The general angle of trigonal bipyramidal, 90 and 120, that's fair game. But like for the more, the shapes where you've got lone pairs on there, I'm not gonna get that into the weeds, yeah.
We don't even know
It's on the sheet, so you would need to like be able to identify which one it is and then look at it, yeah, yeah. Okay, feel free to email with questions. Hopefully that makes you feel a little bit more like, this isn't so bad, it's gonna be okay. I know the first test is always